Good. Good evening, everyone. Today we'll be doing section 14.6 on directional derivatives and the gradient vector. We'll also get into section 14.7 on max and mins, which is neat. But this whole section deals with directional derivatives. So far, we've only done derivatives such as fx and fy. Fx was only in the direction of the positive x-axis. Fy only went in the direction of the positive y-axis. But how about getting a derivative in another direction? And so I thought we'd just start with this problem. It's like one of the first problems out of the textbook. And they want us to estimate the directional derivative at Reno in the direction of Las Vegas. All right? And those numbers in there are in the 50s, those contours, those are temperatures. Those are the actual temperatures. And you need to know the distance. I'm just going to pull this down, slide this down so you can see the scale. Everything was distance was in miles down there. So there's good. I'll leave that there so we can use that. So if we want to estimate the directional derivative, remember we're just going to estimate it. So the best we can do for contours is just do, we're estimating a derivative, right? This is called a directional derivative because it's going in a particular direction. The best I can do here is change in the function, what was it, temperature? Over the change in the distance. That's all we can do in terms of estimating a directional derivative. But yeah, let's find the change in the temperatures and estimate the distance between them. But the wording on this problem, they said at Reno in the direction of Las Vegas. I didn't want you to get so caught up in, oh, I got to know the distance between Reno and Las Vegas. Remember the key is, just like we were doing the tables last section, we use the numbers as close as possible that we can at the point. So they said estimate the directional derivative at which city? At Reno. What's the closest contours we can use around Reno? Looks like we can use the 50, right? And the 60. And if you want on that piece of paper, when it has this, just draw a line that goes from here down to Las Vegas. Feel free to draw a line, all right? Because that's the direction. We're going to go from here to here, but we're going to use these two numbers. So when I'm using my fingers right now, all you need to do then is, along this straight line path, can you estimate that distance? If you need to slide a ruler next to it, just to estimate what would that distance be. I'm going to take my fingers and go like this. Looks like that would be the distance between the 50 and the 60 towards Las Vegas along a straight line. All right, come down here. And I don't know, 0 to 50 miles, 60 miles, it looks like. So that's what I can use for my distance. 50 to 60 miles, I use 60. And what was the change in the temperature? It was 50 minus 60, right? Or 60 minus 50. The key is, did the temperature increase or decrease as you go in that direction? It increased. So what's 60 minus 50 degrees Fahrenheit? It looks like, everyone, here's our estimation of the directional derivative. 10 degrees Fahrenheit per 60 miles. So it appears like the temperature is the directional derivative at Reno in the direction of Las Vegas is roughly 10 degrees Fahrenheit per 60 miles, right? It's increasing that much. And you can reduce that to what? 1 degree Fahrenheit per 6 miles traveled. That's directional derivative. But now we need a formula for this, right? But that's what it is. It's just getting ready to change. You're not just going, like before this section, we only went in the direction of the positive x-axis or in the direction of the positive y-axis. So, hey, I'll turn this off. We may come back to it in a bit just to see some cool things. Oh, I'll turn that thing off. So I'll hit the light, and we need a math formula behind this. So what's the math formula that we can use for all directional derivatives? This is neat, everyone. They use a vector made up of partial derivatives. So let's just say you had a function of x and y. Right? And gosh, I'll just use a simple x squared plus y squared. Here's your function. The directional derivative will be equal to some vector that's made up of the partial derivatives. And all we have to do is put a dot product with some vector. I just want to give you an example. What is the partial is fx and fy here to that function. What's partial with respect to x?
2x.
2x.
Y squared.
Partial with respect to y?
2y.
Well, let's just see. What would have happened, everyone, if I used right here? This is going to be called this vector here. There's a name for this vector. I'll put it on the board in a second. But this vector right here is called the directional vector. All right, it's the directional vector. So let's go back to last section. If we went in the direction of the positive x-axis, do you agree I could just make this a 1 and a 0? Do the dot product, what would you get? You would just get the fx times the 1 plus the fy times the what? 0. So this would be gone, you just have the fx. And see, that would give you the direction, that would give you the rate of change, directional rate, in the direction of the positive x-axis. Of course, what if I used what? A 0 here and a 1, that would give you the rate of change in which direction? So this would go away. If you dot that, you get fy, right? In the direction of the positive y-axis. Cool? But what's so great about this is our math formula. We can do this in any direction. It doesn't have to be 1, 0 or 0, 1. It can be like 1, 1, right? But the key is this does have to be a unit vector. So I'm going to write down the actual formula right now. This direct vector right here, they call it the unit directional vector. It must be a unit vector. This vector here that's made up of these partial derivatives is called the gradient vector. Alright, so that's our math formula. This is the notation for directional derivative. This is the notation for it. The directional derivative will always be equal to, like d with the subscript of u. The subscript of u is there because we always use what kind of directional vector? A unit directional vector. So that's why it has that funny little u there. But that's the notation for directional derivative. This thing right here is called the gradient vector. We take the dot product with the unit direction vector. And they have to tell you which direction we're going. And we'll put that right here. We'll just make sure it's a unit vector. So I'll put it again like this. There's a cool math symbol for gradient vector. It's called GRAD. That's the notation for the gradient of a function. So the gradient vector, it's a vector, but it's the gradient of the function f. What's its definition? It's made up of all the partial derivatives. So we can go off to the side here and leave this up all class. You know, what's GRAD of f equal to? It's made up of just what? All the partial derivatives. Heck, I'll even do an FZ in section in case it has what? Variables x, y, and z. It can have 3 dimensions to it. Cool. There's another notation for it. I use this the most. It's also del f. That symbol's called del f, so I'm going to put that here too. That's del. D-E-L. We just call that del. So I'll refer to del f. When I'm saying del f, I'm talking about the gradient vector. But GRADF, grad f, is also the gradient vector. Gradient of f, gradient of the function. They give you some function. We get the partial derivatives, and you can find out what that vector is. Cool? This is huge, everyone. Even at the end of our course, you'll still be doing this. There'll be some neat stuff in chapter 16 where you'll get this. They'll give you the gradient vector. They'll want you to go back and figure out what this is. And of course, that'll involve integrals, won't it? That'll involve integrals, exactly. So that's what will happen at the end of our course. So this gradient vector is neat. We take the dot product with the unit vector. So here we go. I'm going to ask you a question. Can you find the directional derivative of this function right here at the point, how about 1, 2? And when I want you to do it in the direction of this vector. 3, 4. So can you find the directional derivative of that function at the point 1, 2 in the direction 3, 4? Alright. So there's fx, there's fy. What y plug into the x and the y? So it's really substituted that value. So it's del f evaluated at the point x naught, y naught, dot unit vector. There's your math formula. It's del f dot u. Looks like a curse word, right? Fu. I know, but that's an easy way to remember it. Del f dot u. This is the gradient factor dot the unit vector. So, but that's not a unit vector. So, anybody know a unit vector in the direction of 3, 4?
Yeah, it should be the magnitude.
And then I got to divide it?
Divided,
So
yeah.
divide out the magnitude from this and I'll have a unit vector, right?
Yeah.
What's the square root of 3 squared plus 4 squared?
5.
There you go. Now if it came out to the square root of 13, I'm going to divide by the square root of 13. That sometimes happens. This came out to be a perfect square. Square root of 3 squared plus 4 squared, 5. That's a unit vector. So just be careful and make sure you always use a unit directional vector. I'll plug in a 1 and a 2. Let's see what we get here. What is 2 times 1? 2 times 2. And then dot with a 3/5 and a 4/5. Alright, what do you get? This will be the directional derivative. 2 times 3/5 is 6/5. Plus 4 times 4/5 is 16/5, gives me which is a rate of change.
Also, directional
Also a
derivative.
slope right in that direction.
Okay.
Oh, 22, thank you so much. 6 and 16, 22. Thank you very much.
So, is directional derivative a vector or just a scalar?
Directional derivative is a scalar. Always a scalar. It means derivative. Always think of that word derivative.
Okay.
This right here, think it is a derivative. And a derivative is a slope or a rate of change, so it has to be scalar. But the formula involved 2 vectors.
Vectors, yeah.
One of the vectors is called the gradient vector. And we take the dot product of the gradient vector with the unit directional vector. And this is the vector that they give you the direction.
Oh, yeah, all dot products are scalar, I remember.
Oh, good.
Yeah.
He goes, hey, all dot products are scalar. Is that good? Okay with that one? All right. Hey, this gradient vector, I want to stop and talk about that because it's really interesting. We'll leave some notes on it. And then we'll do a couple more problems where we find directional derivatives. Sound good? We're going to do it off like a hill. I'll give you a hill problem. It'll be cool. But can we just take a moment to talk about this cool gradient vector? All right. What do we know about the gradient vector? First of all, it's always perpendicular at the point of tangent. That's the first one I know about the gradient vector. The gradient vector will always be perpendicular at the point of tangent. It'll always go in the direction it points in the direction of, and I'm referring to, I'm referring to contour level curves. It always points in a direction of the increasing k values on a contour curve where the k values are like the z values, right? Okay. Well, can we get an idea of this? The best way to see this, I'm going to explore this, is just looking at an applet. So I'll turn it back on. Just so you can see this. I'm just going to pull up a nice applet that has the gradient vector on there and everything. Let's see. Just an image that can show us like the gradient vector. Alright, mathinsight.org. At least I can slide this stuff around. And that comes in. I'm just going to slide this thing around here. Let me just pull this down a little bit. Hey, is that showing up? So at that point, do you see this red vector right here? It is red. Do you notice it's perpendicular at that point of tangency off the level curve? But here's the three-dimensional, image of this mountain. But I can actually slide this thing around, but you'll notice no matter what, when I calculate directional derivatives by this formula, and when you can watch this change right here, that right here gives you the directional derivative, you can watch it change. I'll just swing it around, but watch the gradient vector will always remain perpendicular at the point of tangent, no matter what. If I slide this around like this, I can do that. I can move this, but does that red vector change at that point? That red vector is the gradient vector. This other color, I'm colorblind, what color is that? Green? Is it green? Yeah, but that's the directional vector. And so what will happen is, when you do that, you can find the directional derivative in that direction. So here, I noticed this would be going uphill, this would be a positive now, right? You slide it around here, and now it's going to be becoming a negative value. Do you agree? Let me see if I can get can I get the directional derivative to be 0? I want to watch that right corner. Can I get to be close to 0 or so? There it's at 1. Maybe I'll swing it even more, no? Somewhere around, right around there. Somewhere around right there when you can see that the rate of change, the slope would be what? 0. So if someone was standing on this hill and walked in this direction, they're saying the slope would come out to be approximately 0. Where it was really steep the other way. Most important to me that you saw that red vector just sitting there. That red vector is the what? That's the gradient vector. Right? It was just taking the dot product of those two vectors. The gradient vector is always perpendicular at the point of tangent, whatever point they pick. But what way does it point? Because you're like a vector, it can point this way or that way. It would always point in the direction of the increasing k values, which the increasing k values is the value such that these are going uphill. Cool? So that's why this is pointed this way and not that way. Cool? Is that all right then? And we'll work some problems. Turn that off. I'll hit the light. Hey, I want to draw an image now. I think I've got one of these, like on the practice set. I'm going to be at something like this. And you pick the gradient right there.